Good morning and good afternoon, depending on where you are in the United States or overseas. Welcome to this tool training workshop of SimCenter. My name is Hassan Karim and I'm at University of Notre Dame. I will give you a very brief overview of non-CFD part of computational tools today, because that's just going to be the focus, to just get you familiarized with your wind engineering background and what things we are doing. So just to begin with the main slide, it shows you the tools we have. But before I go into those, I just want to show you this broader picture of the background. How do we model wind loads on structures? Because majority of you, I assume, have wind engineering background. Some of you are dynamicists are coming into this. So the basic tool primarily, as you can see in this diagram on the right, has wind tunnel, full scale, codes and standards, and of course the computational wind engineering part. The computational wind engineering part has several subsections, which I'll be detailing a little bit more, like stochastic simulation, data-enabled design and analysis, and the other part is CFD, which will be tomorrow. Just to talk about, most of you are familiar with wind codes and standards, and as most of these codes are reductive formats, and a lot of simplification has been done in those, so they're good for their certain purposes. They may be a little oversimplified and may, in some cases, overestimate results or underestimate results. And for the dynamic part of the things, and also anything, the building fluctuating or the wind fluctuating, it is captured by this very unique feature, the gust loading factor due to Davenport. And it takes care of the buffeting response and primarily for the long wind response of structures. Other building codes have provided some empirical fits to crosswind and torsional effects. NASE 7 offers a data-based approach I'll be talking about. So the question is, we need better ways to overcome or complement conventional code standard procedure to account for more accurate aerodynamic effects on structures. So this is what I call digital wind approach, or a cyber data-enabled design framework. Those of you who are more interested in looking into the details of the process, you need to look at this particular paper, which provides a very good description of how we start from pressure fluctuations on building and resolve them into the loads and the response. So if you look at the first one, is a hybrid combination of wind tunnel acquired data. So the data comes from either wind tunnel or from stochastic simulations or from CFD, and then they are coupled with structural models to create a real-time digital simulation of building response. So that is a basic theme in this one. So the advantage in this one is, because it's in time domain, it has the ability to include any nonlinear analysis, and we have this rich library of tools in OpenFOAM, which is available to couple them. And as some of you already know, that there is interest developing in performance-based design for wind to consider building going inelastic. So that's where the nonlinear analysis part will come. Many times in these buildings, we have to put damping systems, could be a tune mass damper or could be distributed dampers. So once we put that into the structural system, typical frequency domain-based methods may not be that convenient. So the time domain approach becomes also very well. Also, once the building profile is fixed, or if we have the data for various profiles which are close to the choice of the designer and the owners, one can then play without going to wind tunnel again with the structural system to optimize it to get the response. So this thing is a very powerful tool, and some of the advanced design firms are already using similar concepts, and we are trying to make it available to people. So just when I said stochastic simulation, don't worry about this very busy slide. I just want to focus on the blue part. We need to simulate random processes, which is fluctuating wind to begin with, or could be fluctuating pressure. So in that case, a classical approach is what we call a spectral representation. You take the spectra of the wind of the process, you divide it into bins, and from each bin you pick randomly your energy contents and then mix them with the random phase angle, and that provides you a stochastic. This is a very simple definition of that, but these methods can go advanced. They have more complications. If, for example, 1,000 points you need on a bridge, then you have to use some of the methods I've mentioned at the bottom, enhanced methods. But if we are interested in non-stationary processes, like you see on the right, with the gust front factors, gust fronts, then one has to use some more wavelet based or on time frequency approach for those. What is data-enabled design? Basically, some of you who have been in wind engineering have probably seen at Vortex Wind, our website, a high-frequency-based balance wealth of data for various building shapes, and one can utilize those, or synchronous pressure measurements, and they can be combined into a structural engineering model to get the response of the building. This is very efficient, and but there are some of the challenges is that we have a large amount of data. We need a large amount of database, because currently the database we have is limited. But I think with the proliferation of wind tunnels and capabilities and the software available, we in the future are going to see enhancement in the capacity of these databases to offer as much options as possible. And also it works online and on fly, and using cyber-based enabled tools. We have built-in user-friendly web interfaces, built-in analysis and design module, and served via browser. Okay, just to give you a background, what goes behind it. If you have a tall building on the right-hand side, we are going to feed in wind tunnel data or CFD data or stochastic simulation. But remember, when we do stochastic simulation, we are limited to a long wind response only, because we can use quasi-static theory to find loads from wind velocity only in the long wind direction. The crosswind and torsion have other complications, and we cannot use that simple transformation. So that's why we have to go to wind tunnel or CFD. So on the left-hand side, you see a lot of building properties. They can come from OpenSeas or any other commercial package. And then the database is pulled out from, we are basically using TPU wind data or NetHaz data. And then we combine them together into the server where the analysis is done. Those of you who are familiar with our Vortex Winds primarily utilizes a frequency domain approach, and also gives you more like equivalent static loads for the designers to use them in a sort of spreadsheet type program. Now the new generation which we have developed here is purely time domain, so we can do a lot of things which are not possible. Just to give you an idea that I'm not just making up, these two buildings were personally designed by me for the wind, and we did not go to the wind tunnel, and these databases were used, and they are sort of not that typically symmetric buildings. They're both in Seattle. Same way, we have a large wealth of low-rise buildings, and in that case, again, the TPU offers a very large database, and same philosophy goes here. A tall building is a place by. Initially, when we did it for Vortex Wind, we use influence functions for the building frame on the left-hand side, but I think the current one approach is very similar to the tall building. We find nodal loads from pressures and then run into a finite element model to calculate the response of the structure. So I think I'm going to stop here. This is sort of give you an introduction of what is going to happen today. And tomorrow we'll be getting into the CFD part, and I'll give a very brief introduction again tomorrow, and then it will be followed up with more nitty-gritty of what we have. Thank you very much. And if you have a question, you're welcome to ask me today, or you can email me. I'll be happy to respond. Frank?
Go ahead, Frank.
All right. So I'm going to give you a two-part outline here. First of all, I'm going to give you a quick introduction to the SimCenter, and then I'm going to go through the WiiUQ tool itself. So this NHERI SimCenter, we're part of NHERI. We have experimental facilities and rapid facilities that provide data to design safe And what we do is we provide software. That software is available on DesignSafe. It runs on the HPC resources at DesignSafe, but it's made available to you, the users, researchers, practicing engineers, to use in your work. Our mission is to transform through computational simulation, natural hazards engineering research. Our aim is basically, we're providing you complex workflows. We're making them publicly available. And the idea is to facilitate research in regional hazard risk management. Our software is open source. It runs on HPCs, high performance computers, and allows you to do high fidelity simulation using these workflows. And these workflows produce uncertainty quantification. Our design is such that we're developing a framework for building what are called scientific workflow systems. And these systems are producing uncertainty quantification measures in the response. The framework is designed to be flexible, extensible, and scalable so that others can come in and swap out different components, provide their own research. And we're seeding the framework with enough components that allow you to use these applications now. We're releasing applications built using the components. And finally, we're trying to foster through our outreach an ecosystem that fosters collaboration among researchers in the different fields of natural hazard engineering. So quickly, what is a scientific workflow? A scientific workflow, that's these applications we're building. These are applications that allow the users to build, launch, and monitor scientific workflows. So the definition of a scientific workflow, basically we're allowing people to string applications together, and the computer will automatically run the different applications in a workflow, taking the input from one and passing it to another. The software, we're trying to incorporate as much existing software as possible. To do that, we're creating pre and post processors to the existing software. And this is our current state. You know, we've been doing tool training now for the last couple of weeks. We've been doing tool training on 4 applications. WiiUQ is the current application. But as part of our framework, you know, these are just applications. These applications are built using a number of components. And these components, you know, they are invoking, you know, other external applications and external data sources, for example, NatHaz and the Tokyo Polytechnic's database. Further on this year, we're releasing a tool for hydro forces on buildings. And ultimately, we want to do these regional simulations. So we're building this, what's called our RDT tool. And this tool, it builds upon all the other applications we've already built. For example, it'll build upon our performance-based engineering, which builds upon both our WiiUQ and our EUQ application. And these applications themselves build on something called QFOAM. Now our tools execute workflows, and these workflows produce UQ. It's something different that we're doing. So when you get your response, we're not giving you single numbers. You have to understand we're going to be giving you mean and standard deviations for all the output quantities. Now, because we're providing these uncertainty quantification measures, this requires more input from you, the user. You have to identify which parameters are random variables, and then you have to do the additional step of then assigning distributions to those random variables. So that's additional work you have to do. In addition to the work, there's a whole bunch of additional computation that goes on when these things run. You know, we're doing, say, Monte Carlo type simulations. So they're running hundreds of thousands of simulations. So what we do is you try and utilize all the cores in your CPU, but we also give you the option to run these computations on a HPC at DesignSafe. So because we're being able to run the applications either locally or remotely, we break our applications up into 2. There's a front-end user interface, that's the application you see. And then there's this back-end workflow management system. That's the application that actually runs the workflow, as we'll show shortly. So, you know, the front-end user interface, this is the application you see. When you bring up EUQ or WiiUQ, you'll see something similar to this. And then it's the back-end, where the user interface is just going to create the input file for the back-end and start the back-end running. And then when the back-end's done, it gives the results back to the front-end. And I'm going to demonstrate that a little bit later. In this talk. And as mentioned, we're really trying to build community. We do that through our workshops. We have tool training events. We have a programming bootcamp coming up, which is an intensive. When we do it in person, it's a week-long course. This summer, it might be a two-week online course. We also release educational applications. And finally, and quite importantly, if you want to have a look at the state-of-the-art report, here we have different faculty members advising on what is the state-of-the-art in the different parts of natural hazard engineering. And of course, we need your feedback. Feedback is very important. We're now releasing tools, and the future direction that these tool takes, you know, what features you would like added to these tools, that depends on you. If you want to provide feedback, you have to provide it through our forum. Don't bother sending me an email, because I'm just going to direct you straight to the forum. So have a look at the forum. If you encounter problems when you run the tool, post the questions on the forum here in the different tools. So now let's give you an introduction to WiiUQ itself. We're going to do this with a walkthrough of the tool. Then I'm going to show you what happens when you're actually running the tool. And then finally, I'm going to go through the various options available to you when you run the tool. So quick motivation, why do you want to do UQ in wind engineering? I like the quote by Jeffries, that uncertainty is as important a part of the result as the estimate itself, and an estimate without a standard error is practically meaningless. So if you're just getting a single number for your simulations, it's really meaningless. You have to know what sort of errors associated with that number. And that is something only doing a UQ analysis will give you. And if you need further reasons for needing to do UQ in wind engineering, there's a pre-standard for performance-based wind design coming out, or it's out. If you have a look in there, they talk about performance-based engineering and needing to do numerical simulations and generate UQ for the results. So the wind engineering tool itself, the important thing to note is this thing up here at the top. Basically, we're trying to quantify the uncertainty in the building response when that building is subjected to a wind event. We do this by performing multiple linear or nonlinear time history analysis. We're not dealing with analysis in the frequency domain. This is nonlinear or linear time history analysis. So right now we're currently heading towards version 3. The current version we released does sampling, stochastic loading, wind tunnel, and takes the data from the online data sets. Version that you're available to download now also includes sensitivity and reliability in the application. And by the end of September, we will be coupling the FEM with our CFD simulations. Right now, when we do a CFD simulation, the structure is rigid. It's a bluff body. As I say, by September, we will be, the building will be moving with the CFD simulation. But the interesting thing about this wind engineering, there's a host of areas that for young faculty and postdocs, research opportunities available within wind engineering. We're listing a couple here. And with these, you know, our tool allows you to play with the different components. Because you can introduce new components, you can do your research and then add, if you're building an application, you can add it into this tool and make it available to other researchers to use. So the workflow application selections for WiiUQ. The important one is basically the events. Where are the wind events coming from? Where's the wind loading coming from? We have a number of different options available. There's even more than that I'm showing here. And I'm going to basically demonstrate this when I go through the different tool. But these are the different jigsaw pieces that we make available when we're running WiiUQ. And for each jigsaw piece, you're going to select an application. And we're going to talk about the CFD stuff. That's tomorrow and the third day. So now I thought I'd do a quick demonstration. What I want to do is demonstrate the tool using a 9-story building. And I'd really like to familiarize yourselves with the interface. And I'm going to go through this example again for a 9-story building. So let me end the show here. And now I'm going to pick up start the tool itself. Let me resize the tool to the full screen before Matt sends me an email message. So this is WiiUQ when you start it up. As I say, there's some selection things down here. These are our jigsaw pieces. As we go down here, It brings up different main panels. This is our, the event. And I said we have different options available. So that options available, there'll be a pull-down menu at the top of each panel in which you can pick from the different applications. So when I go in here, I'm basically picking different applications to choose from. I'm going to go now back to, say, stochastic wind application. Down here at the bottom, we have our buttons. If you want to run the job locally, that's this run button. If we want to run the job at the HPC at design safe, that's going to be run at design safe. And then we've options to get the data from design safe when we run it there. And of course, we want to exit the program. And to run at design safe or get information from the design safe, the first thing you have to do is this top right over here, we have this login button. You need to log into design safe. And the status while the tool is running and things are happening, there's a little, if there's an error message or a status message, they will appear up here in this part of the screen. So then let me quickly demonstrate this for this 9-story building. So I'm going to first go into this UQ panel. I'm going to leave everything alone. I'm only going to do 20 samples. If you're doing a real research, you want hundreds, thousands, tens of thousands. For our thing, I'm going to specify I've got a 9-story building. This building is the LA 9-story building in the FEMA 355C report, if anybody's interested. So this building is 1440 inches tall. It is 1/800 inches wide and 1/800 inches deep. Plan area I'm not going to care about. So now if I go into this next panel, the sim panel, this is where we're going to create our structural model. So now you see I've got my 9-story building. The story heights will give me that total height. So I'm going to create now random. Remember, we need random variables when we run this tool. So I'm going to specify that my floor weight is a random variable. And I'll also specify that the stiffnesses are also random. Like I don't know what they are exactly, so they're just going to be random. For my event, as I say, I'm just going to stick with stochastic wind, but let's play with this gust speed. So this is the 3-second gust speed at 10 meters height. I'm going to change, let's just make this a random variable. Call it gust wind speed. There's back to the sim tool, something I forgot to mention. In this table here, I can play with or modify the properties for each individual floor or story. And you see which one is, when I click in it, it'll kind of highlight where I am. So let's go on to so that's the event. The event I'm going to do is the stochastic wind, my finite element model. Here, an important thing I want to make, by default, it does mass proportional damping. I want to make sure I'm using Rayleigh damping, and I want to use the first 6 modes. So this will give me Rayleigh damping. For my EDPs, I'm just going to pick the default random variables. Now here I have to specify values for these variables. So the wind, 1200, oh sorry, 120, stiffness is 2200 kips per inch, say 220. And the gust wind speed, oh, let's say 20. We'll give it a standard deviation of 3. And I hope those parameters are right. So now that I've entered all my parameters in the different panes, I just quickly go through to check that I've got stuff in all of them. Then I can hit the run button. And now we're running the simulation. So this will take a few minutes. If there's any errors or something happening during this simulation, they would pop up here. If I got the parameters right, this should be ending about now. There we go. So here's the results. For all of these response quantities, I get a mean, a standard deviation, the skewness, and the kurtosis for that response quantity. For example, my roof, my interstory drift is very small. My peak floor displacement is 0.4 inches. I've got my root mean squared acceleration is 1.7, and the peak floor acceleration is 6.9 inch per second squared, and I see the standard deviation for those quantities. So that's the summary. If I then click on the data values tab, I can start looking at these things graphically by clicking in the different things. Or if, I can see if I left click and right click in these in the data columns. You have to be in the data itself. You right click in the data. You know, I can see how my acceleration, for example, in the first floor is changing with the gust speed. If I want to see how it does it with the say with stiffness, how it changes with stiffness. You know, I see a slight, you know, it's coming down with stiffness. As I increase the stiffness, I think my RSA is coming down. If we go out to all the way over here to the 9th floor. So now if you right click and left click in the same column, we start seeing sort of probability distribution functions or histograms of the response. I've only run 20 simulations, which is why the histogram doesn't look so good. If you look in the documentation, you'll see this run for a lot more simulations. So that was left clicking in the column, then I right click and I'll see the CDF again. Look at the documentation for a better CDF because I just haven't run enough simulations. So that's the tool. That was it running. And I've just exited again. So let me now go back to the presentation.
May I interrupt you briefly? There was a question on the chat about the use of SI versus English units. Any plans or any advice?
You can pick either SI or metric. We switch between the two. The demonstration, the example at the end that I have in the presentation is done in the metric units. So now let's talk about what happens when I actually run a workflow. So as I mentioned, we've broken the tool into two parts. We got the front end and the back end. The front end is that part I was just demonstrating. It's the back end where we're running the uncertainty quantification. We've got this UQ engine that runs these workflow and it runs it multiple times. Each time it runs it, it passes to the workflow this parameters file, which contains what the parameters are for this deterministic simulation, and then the workflow will produce a results.out file. More graphically, you know, here's what ultimately is happening. You launch the workflow, it reads some applications file, it creates this folder, temp.simcenter in your documents directory. It writes the input file for that workflow driver, then it launches that workflow driver with that input file. That workflow driver basically creates the input files for our UQ engine, then it launches the UQ engine. We run multiple times, we get the results.out. And when the whole thing's done, it returns with control to the user interface, which then reads the results and presents them to you. So that I thought I would demonstrate with another demonstration. So now I'm going to do a 3-story building, and I'm going to change things up just a little bit to show you some of the other features in the tool, but I'm not going to change the units just yet. So let me go back to the tool. So here's WiiUQ. Something I didn't mention in the previous, at the top right, depending on whether you're, depending on if you're a Mac or Windows, you've got a file open, you can file open. So I'm going to open a saved case, so I can open and save all my files. So I'm going to open a file. And I'm going to open the one I was playing with earlier, which is this 3-story sensitivity.json file. So this will just save me having to run through all the inputs here, but I'll go through them with you. This file is actually currently running a sensitivity. Let me quickly change it back to a forward propagation problem. So I'm going to just do, let's just cut down the simulations if I actually run this. So we're going to do 10 simulations this time. So this building is a 3-story building. It's 468 inches high. Width and depth are shown here. And these are the defaults. Remember, you can change the units. It will not change these numbers, but it will, it basically, the that information about what units is in will be passed to the backend workflow in that dakota.json file. So when the input file going to the backend workflow, we keep track of the units. So there's the units. Now here I'm doing something different. I'm not doing that 3D structural model. Basically now I'm going to use an OpenSeas example. This example you have in that examples directory that I left on Design Safe for you. This example has 4 nodes, 1, 2, 3, 4. So you have to specify what those 4 nodes are. This is so that I can determine which, when the event runs, it creates wind loading for each floor level. And I need these centroid nodes tell me which nodes to apply those loads to. And then also the response nodes. I need to know where you want to look at the response. For this case, this model has 3 NDM. The spatial dimension is 3, and it has 6 degrees of freedom at every node. The event, this time I'm using TPU. So these are the options that pop up for the height and width. I'm just going to use 2/4. For my depth to width, I'm going to use 2/2. Now my building, of course, does not meet these dimensions exactly, but these are the closest we could find. So that is a limitation of when we use the TPU database. The building might not fit exactly with your building dimensions. And then for my wind speed, I'm going to create a random variable again. I'm going to call it min wind speed. So instead of the gust wind speed that was in the stochastic motion to stochastic event, TPU takes a min wind speed at the 10-meter height. Again, for the finite element options, I'm going to use Rayleigh damping. And because this is a linear problem, I'm just going to switch my algorithm to linear just to save some time when it's doing the simulation. So there's linear solution algorithm. I could probably speed it up again if I change the solver. I don't need a sparse solver for this problem. I'll leave it alone for now. So here's what I'm going to do. Again, different. So I'm going to, instead of getting all that output that we saw in the 9-story building, I'm just going to look at, say, the nodal displacement. And all I care about for this result is what's happening to the displacement of the roof. If I want, I could add, say, let's add so now I've added the root mean squared acceleration also at the roof. And just for the fun of it, let me add the force at the element at the base, and I'm going to get it in so it's the shear force. I could also ask for the moment if I wanted to, which would be the base overturning moment. My random variables, these are the random variables. I'm throwing in a dummy one here. This is because I was doing a reliability analysis or sensitivity analysis, and I wanted to see what the effect of dummy had on the response quantity. So there I've gone through and I've set up my thing. Again, I'm just going to run 10 simulations, say. I will click the run. Now this might take a little while longer than the previous one. The reason I'm having to go off now to Tokyo Polytechnic's online database, I'm asking their server to give me the results for that particular wind tunnel experiment. I'm downloading that wind tunnel data, now computing the forces, and then I go off and do the simulations. So again, now I see, I'm just getting the quantities for those response quantities I was interested in. Again, if I wanted to plot them, I could. Again, I've only got 10 points, so there's probably not too much stuff going on. So right clicking and left clicking gives me different stuff. Again, I just don't have enough data, I'm sure, here to, well, again, there's the displacement going up with our wind speed and coming down a bit with our story stiffness, and all over the place with the dummy random variable, which is kind of what we want. So let me go back and I'm going to just start something running, and I'll come back and get the results later, because this does take a while. So I thought I'd do a sensitivity analysis. I'll leave that alone. I have to go in here. I'm going to remove one of these EDPs. The more EDPs I have, the longer this takes. So I'm just going to look at it for the say displacement at that roof level, that peak displacement. Leave that alone. TPU again, 4 nodes. Yeah, that's everything's all right. Okay, so I can run this. And this will take a while, so I'm going to go back to my presentation. Okay, here we are again. Oops, daisy. I meant to do something else while I was in there. So the real result of that thing, I wanted to look at these files. So let me look at these files as this thing is running along. I'll go to this. So if I go to my documents folder, I can spell documents. I go to my WiiUQ folder. So when you run this tool, we're going to create this directory for you. And then when you run it locally, you're going to have this local workdir. And when we run it, remember we're creating this directory called temp.simcenter. So in temp.simcenter, we have stuff. So that, there's the tool running. It's creating all these. Each sample it creates a new workdir and starts running in that workdir. The additional directory where it puts everything initially is in here, and this is what runs the workflow. There's that workflow driver. This is the file that this management system creates to actually run our workflow. So at every step in the workflow, it's going to perform all these. It's going to invoke all these different applications to do stuff. So that's that workflow driver file here. That mat file is the result that came back from the TPU database. I've had to take that MATLAB mat file and convert it into a JSON file so these applications can read it. And there's that Dakota JSON that defines that's the input that the backend receives. If I quickly look at that file, you'll see it. It'll list all the different applications we selected. There's that low-rise TPU. That's the wind event. I was using the OpenFOAM for the input for that sim model. And then for each thing further in that file is, there's those information about what the parameters were. For example, there's those random variables. I had the dummy random variable, the story stiffness, my mean wind speed. They were random variables I selected. There's my response node. So all the different entries you made in the different pieces are actually put into this file. This directory, while it's running, I'm up to 99 or 150 simulations now. But there's a couple of files here. Dakota.in is the one that we launched Dakota with. I mentioned that when I was going through the presentation. So Dakota is currently running, and that was the input file for Dakota. And as it runs, it creates the output file and this tab file. And these files, once they're done, when the thing is run, this is what the user interface, these are the two files the user interface is going to load. Okay, so let me now go back to the slideshow. So now basically I was going to quickly demonstrate the different options that are available to you. For the sim, we've seen two now. We saw this multi-degree of freedom, which is this nonlinear shear building model, and OpenFOAM. With OpenFOAM, you can put any finite element model you want in there. It does not have to be a shear building. So we went through the interface for the MDUF. I went through it quickly. Two things I probably should have mentioned is that if there's a mass eccentricity, or you want to look at record the response at the corners of the building, there are options in here that allow you to do that. You give the mass eccentricity for the different floors, and also the response eccentricity. So I'll record the results here if that's what you specify for your response eccentricity. By default, all the results are for the center of the stiffness. And as I mentioned, you can go through and each of these represents a story or a nodal mass, and you can go in here and edit the individual quantities directly. When you go in here and edit, it should highlight which story or node you're dealing with. The OpenFOAM script, this is the one I ran a 3-story version, but this is a 9-story version of that same 9-story building model. And when you do this one, you create a whole bunch of additional nodes. These nodes are, again, the centroid nodes and the response nodes. So this is a 10-noded model, so I have to specify the ground floor through the roof. I have to give, tell the computer tell the program which node corresponds to the different floor levels in my 9-story building. So I've got 10 nodes for a 9-story building is the important thing. And this is the tickle script. This is the OpenFOAM input file that will quickly generate a 9-story shear building model. I'm using an elastic beam column element instead of zero length, just so that I can get out those base moments. This model is not doing P delta. You could quickly modify this to include P delta effects. We do have the weight for each floor. You could create a nodal load, add the weights, and then the geometric transformation, instead of being linear, you'd specify you wanted P delta, and then we'd get the P delta effects in our results. The options for the EDP, again, we've seen both of these now. The standard win, you get a whole bunch of outputs for every floor. You get the peak floor acceleration, the root mean squared of the floor acceleration. We get the peak floor displacement, and we get the peak interstory drift. That's for every floor. And the stochastic only had one direction. The TPU, for example, had 2 directions. So we can get these for each floor, and then we get it for each direction as well. So we'll get it for a 1 and a 2 direction. So this little thing here, the peak floor acceleration, the 1 represents the floor level, and then the second 1 is the direction. So the user defined, again, I did this. The option, we specify the special input file we want that's going to create the output that our post-processing script here is going to read. So this is the basic, what's called the recorder in OpenFOAM. This is the recorder script that will be added to just before the analysis start. So this will start recording all this information, the displacement, acceleration, and the forces for the nodes and the elements. And then we've also got this post-process script, and this post-process script is going to understand what these quantities are, and based on what's the outputs and what these quantities are, it's going to create that results.out file. Remember that results.out file? That's what this script is going to create. So let's say here's this post-process.tickle script. Is creating this results.out file. It's reading in the different displacement.out, accel.out, and forces.out. So these are the output files that those recorder commands created. So when the analysis is done, we read in those files. We're going to create a results.out, and then depending on the quantity of interest that you've specified, what are the EDPs, you're going to this script is going to go figure out what you wanted and then put it into that output file. And then finally, it closes the output file when it's done. This can be done in either Tickle, or if you prefer Python, you can do it in Python as well. And again, as you've already seen, that the output is now limited just to what you specified. So the options for the finite element, we were playing a lot with the Rayleigh damping. By default, remember again, it's initially modal or mass proportional damping. If you want to get Rayleigh damping, you want to add, for this mode 2, you want to specify what that second mode is. The algorithm by default is Newton. If you do have just an elastic problem, running linear will speed up the simulation time. And another option for the damping, for example, is modal damping. If you use modal damping, you have to use Newton. Don't switch to the linear algorithm. With modal damping in OpenFOAM or pretty much any finite element code, you need to use the Newton-Raphson algorithm. And I can also specify I want to use my own analysis script. I don't want to use the defaults. I want to use my own. And here's an example of an OpenC script that would do a nonlinear dynamic analysis. So the options available for UQ, we've looked at sampling. Sampling, where we've got a whole, we define a distribution for our random variables. We run the workflow driver multiple times, and then for each quantity of interest, we get a mean, standard deviation, kurtosis, skewness. And then, as I showed, you can see the CDF. You can also look at the histogram of the response. To date, I've only played with the Latin hypercube sampling. I didn't show you the Monte Carlo or the importance sampling. Or we have two other options available: polynomial chaos and Gaussian process regression. These two are surrogate methods, so if your simulation takes an awful lot of time, you can run fewer simulations using these surrogate approaches. Reliability methods, I haven't demonstrated that in this presentation. Again, the idea is we've got our random variables, and what the workflow driver is going to do, instead of giving you for, if we look at the CDF, instead of coming up with the whole CDF curve, you just specify what values on that CDF you're interested in, and the tool is going to respond that for, well, for example, for the minodal displacement at the roof, and you specified I want the 70, what's the chances of what's the probability that will exceed a certain value? The application, when it's done, will say that, well, for value A, you have a probability of, say, 70%, whatever quantity of interest you work with. The important thing to note when we're dealing with reliability, you only can specify one EDP value. So again, one EDP value, this will not work, for example, for the standard wind EDP, because it just produces so many response quantities. Right now, this program is limited to using one EDP value. And later on today in the documentation, there'll be an example showing the reliability for that 3-story building model. Sensitivity, this is the one application, this is the thing I just ran. Again, we gave it the random variable distributions. My workflow driver is going to run multiple times. And for what it's going to produce is, for each quantity of interest, it's going to tell you what the Sobel indices are for each random variable. These Sobel indices are a measure, or they give you a measure of how much that response, the random variable, is affecting the response. And then here are the options for our random variables. Let me go back to the tool again. So just say this thing is run, for example, remember we just did our sensitivity analysis. And here are for our, we remember we're just looking at displacement at the roof. Displacement 4.1 is displacement at the roof. And here are our Sobel indices. We also threw in this dummy random variable. So as I say, this dummy random variable has basically no impact on the influence on the response, which is what we'd expect. And we see that the mean wind speed has a much larger effect than the story stiffness on the response. But they do both contribute to the uncertainty in the response. So let me go back to my presentation. And as I kind of suspected, I wouldn't have enough time to do this one live. If you come to the workshop, if you come to the afternoon session, I might do this one live. But this is a quick building I put together, 30 by 30 by 120 meters high. So I'm using metric units. I set it up for a 3-second period. And the results here, I'm going to show it for forward sampling. I'm using the DEDM HRP, that's vortex winds. I'm using the OpenC's, Rayleigh damping, and then the user-defined. And what I'm looking at for the user-defined response quantities are the peak roof displacements and RMSs of the accelerations, also the peak base shear and peak overturning moment. So here's what the UQ panel would look like. So this is what would, almost by default, I've changed the 10 or 20 to 100. If again, this is just for demonstration purposes. If you're really wanting to look at the UQ and the UQ in the response, you'd specify more than 100 samples. For the GI panel, it's 30 stories, 120 meters tall, 30 by 30. And here I'm specifying kilonewtons and meters for my units. So again, I'm switching to metric. I'm using this OpenC script I had, the smaller building. It's in that examples directory. This is somewhat tiring. I had to enter all the nodes 1 through, remember 31 is the last node. That's the node at the roof. 1 is the node at the ground. So I have to specify all 31 nodes. 3 spatial dimension and 6 degrees of freedom. I pull down, go into my events. I'm pulling down the load generator. I select the EDM HRP. It automatically identified that I had a 1-to-1 ratio and that the building was 4-to-1 on the height ratio. So they were automatically selected when I came in here. And then I'm just going to say I've got a mean wind speed for my, I'm going to create a random variable for the wind speed. Vortex wind, the wind speed is the min wind speed at the top of the building for whatever duration you're giving here. Right now I'm just doing 10 minutes. Next slide. On the FEM panel, I probably should have switched to linear, and I did 10 modes. So I'm really damping the first 10 modes. And these are my response quantities, the displacements at the roof. Remember 1 and 2 degrees of freedom direction now, because I'm going to get wind forces acting in both directions. And also, you'll also get a torque on the building at each floor from vortex winds. I get the forces, so these are the base shears, forces 1 and 2, and then 4 and 5 are the 2 moments. Random variables, min on the wind speed. I've specified my story stiffness. I've got a 10% on the story stiffness, 10% on the wind speed, and it's like 8% or so on my rho, which determines the building weight, and then from that we get the floor weights. And then finally, I look at the results. I get the results for the individual response quantity, and then we can start looking at things graphically. Again, we're seeing sort of the same things. The displacement goes up with the mean wind speed. The displacement comes down with the story stiffness. And then you can start looking at the frequency distributions for the different response quantities. And then the exercise I have for you to do, if you're interested, before we come back this afternoon, is in the examples directory. I have a whole bunch of different building models. I suggest you pick a building model and then just repeat some of the things I did. Maybe do the sampling and the reliability for that building, and we will go through it this afternoon. So with that, I'm done. We've no time permitting. I'm out of time.
All right, thank you, Frank, very much. We're almost out of time, but there are a few quick questions if you and Hassan are willing to take them. The first one is a question about about units. So yeah. For the building dimensions, is there a place to set the SI units? Or
yeah, we did that. I did that in that last presentation, the last part of the presentation. Here's where we're setting the units in this little box here in the general information. You know, these are the force units available to you, and the length units.
Okay. And is it possible to use non-regular structures, so non-regular floor plan geometries?
Yeah, of course. Well, yes and no. Yes, in the sense that you can put in an OpenC's model for whatever building whatever your building looks like, but then when you come to the events, most of these are just limited to rectangular or not rectangular or block structures. If you have your own wind tunnel data, you could use a wind tunnel experiment, or if you just wanted to, if you knew what the time varying forces were at the different floors, you could actually add it as what's called an existing SimCenter event. So again, for the irregular shaped building, you might be stuck with just using a wind tunnel experiment or the existing. I don't think stochastic wind currently would vary none of the others would currently vary the thing. Of course, you know, we'll get to tomorrow for the expert system, if we're doing a CFD simulation and your model for the building was you could model the building whatever way you wanted using the expert system. Next
Okay.
question.
Yeah, and then the last question is dealing with probability distributions and values for the mean and standard deviation.
Yeah.
Do you have any, where are you getting the estimates for the mean standard deviation, and what sorts of probability distributions do you assume?
Well, these results, if we go back to the, I don't get it in this one. So the random variables, the different distributions, I was always dealing with normal. We have a number of different options available. If you want to have a look at what each one looks like, you see that. You see that. For actually calculating what the mean, standard deviation, kurtosis, and skewness is, that's just mathematical expressions. Basically, we get for each sample. Let me go to the results out. Let me go quickly here. So there is this file, Dakota tab.out. And here are the results for every sample that was run. We have our random variables, and then we have our response quantity. In this case, I was only looking at displacement at the 4th floor at the roof. So we have all these values, and all we're doing is doing the statistics on these computed values. So that's where those statistics are coming from.
Frank, the question may also be looking at the, how do you decide for the PDF or the mean and variance of the input parameters? So I think the answer for that is that there's a lot of information available in the literature.
Yes.
Where you want to make sure that a process, for example, strength, which is always positive, like the compressive strength or the yield strength.
Mm-hmm.
So you know typically have log normal distribution for those, so that everything remains positive.
Right,
You don't want to use Gaussian distribution because that will give you negative values. But there are a lot of papers on wind structure interaction under uncertain conditions. My own, there are several, which lists a long table of what we have found based on looking at the data. What are the good parameters or distributions for the input values?
Yes. And also I might suggest, if you go look, this will take you back a time, go back to how they came up with the guidelines for the LRFD. A lot of work by Galambos back then, figuring out what were for the load resisting factor design, what were the random variables, what are the distributions. If you go look at his work, you'll see where all that, a lot of information there can be found in there.
That is one of the earliest reference you can find. Very good one.
Yeah. Is there any other questions, Matt?
There's one more question about if the DEDM HRP is based on the TPU test data. How are these two inputs different?
Well, right now we're just, for the TPU, we're just looking at the low-rise TPU. DEDM they do the high-rise building. And it also, they calculate the forces for me directly. I don't have to calculate the forces. But they're different data sets. One's high-rise and one's low-rise.
And TPU has a very large number of low-rise configurations.
Yes.
But for high-rise, these are the limited one which you can see. And we are hoping that other groups would be developing some of the generic building shapes, and we'll have a larger pool to pick the values. And I think this can also be supplemented, hopefully, down in the future with the CFD numbers also. So people will have available to them the wind tunnel data and the CFD data also. We're very hopeful this will happen soon.
Great. Well, Hassan and Frank, thank you very much for your informative presentations and for introducing the wind engineering with uncertainty quantification application. We conclude today's presentation and invite people to attend tomorrow's training, day 2. And we look forward to your participation in office hours later this afternoon. To the participants, thank you for your attendance and for your questions. And again, thank you for attending.